Hey classes, welcome back. Just a quick overview here at week 27 of where we've been, where we're going. We just wrapped up a little bit with Hawaii. We did Hawaii for a number of reasons. One, being an isolated island chain, it's one of the places where we can see the effect of invasive species on an ecosystem. Hawaii, more than most places, has been impacted by species coming on in, things like rodents from ships from the age of European exploration, that then would go to the island and do things like eat the eggs of indigenous birds that weren't used to predators that would be destroying their eggs on land. And you had many species of birds, not just in Hawaii, but throughout the Pacific, going extinct before modern science even cataloged them. So it's a good example of an ecosystem that is very, very delicate. And then also with our rock cycle, we did a little bit with, for example, this right here, basalt, which I'll get to in just a second in terms of one of these pictures. But the entire island almost is entirely made of igneous rock. And so you're looking at brand new land down here, but as you move to the northwest, by the time you get up to Kauai, you're looking at land that is almost 5 million years old. And you notice generally as the islands go to the northwest, they get smaller. And you get way out there, you get to Midway, the atolls that are barely sticking up over the surface of the ocean. Later on, too, we'll be talking about Midway, so I wanted students to see it when we talk about the growing ocean plastic problem, human waste in the form of plastic garbage ending up in the Pacific in these giant gyres and really all over the world. And Midway Island, they are constantly collecting plastic, which is impinging on the wildlife there. So a lot of times when we look at the Hawaiian Islands, also, we did a little bit of a math tie-in. Your math teachers across the hall do speed, distance, time, rate problems. And if you're looking at plates moving about 2 inches per year, it's just an average. Some move a little faster, some a little slower. But if you're moving about 2 inches per year, you can do calculations on when did the Atlantic start opening up and how long will it take for Hawaiian island chain to make its way all the way up to present-day Japan, or a little bit north of Japan, actually. And if you're looking at the pictures here, this is a picture of Castle Peak up in the Sierra Nevada. This is where this rock came from. This rock was collected just about where this picture was taken, just a little bit back from where this picture was taken. The basalt, the igneous rock that you see here, is all over the Sierra, along with the granite. Granite and basalt are very similar chemically. They just cooled at different rates. When you look at this picture down here, you're looking at Montara Mountain, local mountain here. Montara is made of granite from the Sierra Nevada. How did that Sierra Nevada get here? Well, when you're looking at the little piece, our little piece here in Pacifica of the Sierra Nevada, you're looking at a piece that, if you check out this picture, taken from the ridge just above Pacifica, the San Andreas Fault cuts in this direction roughly. Currently, we're on filming. This is right about there, Ingrid B. Lacey's school. The San Andreas Fault goes offshore, if you will, right about there at Muscle Rock. And the part of the plate that we're mostly on the Pacific plate here, has been moving north for about 20 million years at the breakneck speed of about 2 inches per year. And it's brought this little chunk of the Sierra Nevada all the way from the southern Sierra, just north of present-day Los Angeles, to where we are in another 20 million years. Excuse me. We'll be up by Oregon, and right here will be present-day Los Angeles. So LA and San Francisco will be right next to each other. So when we're looking at these, let me turn off the screen here and show you the next part. When we're looking at these right here, we are looking at some of the long changes, some of the changes that take place over a very long time. So we're looking at the long evolution of life on Earth. That's one of the key takeaways from that unit is life needs an incredibly long time to get to where we are. Everything from the Cambrian explosion about 500 million years ago till right now. But it has a very long time when you look at the geological history of the planet. Our key terms for this week have to do with chapter 14. And you might notice that if you're looking at the CPO book, we go from chapter 12 to 14, and we backfill chapter 13. The reason I do that is because chapter 13 is generally about, it's all about fungus, the fungi kingdom. And I like to do plants before fungus because when we're looking at these right here, we're looking at tree cookies, we're looking at the things that decompose trees, put the carbon back into the atmosphere. We want to think a little bit about the carbon balance in our atmosphere. Photosynthesis, for example, is one of the very first chemical reactions that we learned about in this class, and we're going to go into that in more detail when we talk about trees sequestering, big word there, it'll be on the next screen, sequestering the carbon in the atmosphere. And you'll hear sequestering, drop my glasses, you'll hear sequestering quite a bit when we talk about taking carbon out of the atmosphere and what we're doing, what humans are doing. Remember, one of the key themes in this grade is the human impact on the environment and how humans are upsetting this balance. So our key terms here are about half of the key terms from chapter 14. They deal, of course, with plants and flowering plants in particular. And I love it that it happens to land just about in springtime around here. We've got a lot of flowers blooming outside, which is awesome. And then finally, on the last screen, let's get a little bit more into that sequestering thing that we were talking about a second ago. The students were asked to write this down today. This should look very, very familiar to most of the students. This is the photosynthesis equation. Ooh, I forgot a 6 over there. That should be 6 O2s to keep it balanced, to pay attention to the law of conservation of mass. But anyway, when you're looking at the photosynthesis equation right here, one of the very first, and I would argue the most important chemical reaction that we learned in this class over the course of the year, and the ways that we are putting carbon into the atmosphere at a faster rate than has been put into the atmosphere in recent history. When I'm talking recent history, I'm talking over the last couple of million years, is by not only burning the fossil fuels. We saw that a little bit when we saw October sky. We talked about this sedimentary rock right here, this coal, and I talked about this chunk of coal, which happened to come from my grandfather's backyard in West Virginia, to burning forests. When we talk about the burning of forests, deforestation, we're adding carbon and carbon dioxide to the atmosphere at a faster rate than it would naturally be accumulating. That has happened several times in the long history of life on Earth. But the big difference right now is we're adding carbon at a rate that is faster than life can adapt to it. Our atmospheric composition has changed drastically over the 4.5 billion year history of the planet. But when it comes to life, life depends on slow changes over time to avoid those big mass extinctions that we've talked about. And then finally down here, the burning of fossil fuels is something that we're going to get into once again in chapter 14, because when we're talking about the deforestation and the adding of carbon dioxide to the atmosphere, we're going to talk about not only the consequences in terms of the radiation being kept in and warming up the biosphere, but what can be done about it? In other words, geoengineering, how can we sequester some of that carbon that's being added right now to kind of counterbalance the effects of adding CO2 to our atmosphere? So just a quick overview of where we've been and where we're going. We'll get a little bit more into the rock cycle as well and talk about some of the very creative ideas for storing excess carbon in ground supplies. For example, marble right here, this piece of marble. Marble used to be limestone. And you might remember that limestone, sedimentary rock, made from calcium carbonate, living things for the most part, made from things with shells. This is a carbon store right here. I'm holding, you can kind of think of it as frozen carbon. So we'll talk about some of the creative ideas for balancing the carbon input to our atmosphere that humans are adding. That's where I'll leave it today. Have yourself a good Monday, and I'll see you back here in class.